Okay, now we are ready to look at the next problem. And the next problem is problem number 5, 11310 OFB. This is an interesting closed type of problem. What we have is we have a rigid insulated tank divided up into 2 compartments by a single partition. One of the compartments contains 8 kilograms of oxygen at a temperature and a pressure. The other compartment contains 4 kilograms of nitrogen at a temperature and a pressure. The partition is then removed and the 2 gases are allowed to mix. We are asked to use the perfect gas mixture model to determine that the mixture temperature and the mixture pressure after equilibrium has been reached. And so this is a binary mixture problem. And so if I were to go to our test app or go to our thermal fluids, it is a closed system, but it is a mixing process. And so we have 2 gases that are going to mix together. And so we look at what choices we have in the substances. And basically we have a binary mixture in this particular case, and we're going to treat them both as perfect gases. And so with that in mind, we select this. We then go to the HTML. And now the first thing we have to do is we have to identify which of the 2 gases is A. And we'll go ahead and allow the first one to be designated as A. And we see that the first one in this particular case is oxygen as a gas. And the second one, the second substance, is nitrogen gas, or N2. And so we are going to allow state 1 to be the left-hand side, or the oxygen fluid A, and we're going to allow state 2 to be the initial condition associated with the nitrogen, and then we're going to allow them to mix and form a state 3 as a mixture. And so just like we did on the 4th problem, we now have to, because we think of this as a binary mixture, if we start with state 1, what we want to do here on the mass fraction, we want to say the mass fraction of state 1 is all A and no B. And so we do that by selecting 1 as the mass fraction associated with oxygen. And so state 1 is the state of the fluid that's in the, let's call it the left-hand side of this volume. What we know is that left-hand side has a certain amount of mass, and the amount of mass is 8 kilograms. We also know its initial pressure of 100 kPa. And we also know that its initial temperature is 42 degrees Celsius. So it is oxygen at 1 bar at 42 degrees Celsius. And so what this tells us then is 6 or 8 kilograms of oxygen would then occupy about 6.55 square meters of volume. So this is a fairly large tank, or at least that side of the overall tank is fairly large. Now we want to go to state 2, and we're going to say state 2 is the nitrogen side. And so in order to specify it being nitrogen, we say that there is no oxygen. And so we use the same variable, but we set it equal to 0, implying that nitrogen is 100%, or a fraction of 1. We know that there are 4 kilograms of the nitrogen in this vessel. And we also know that the temperature is 20 degrees Celsius. And we also know that the pressure is equal to 180 kPa. And so under that temperature and pressure, 4 kilograms of nitrogen would occupy about 1.93 square or cubic meters of volume. So we have our initial states for our two substances that are initially separated. We then now go to state 3, and now what we know about state 3 is that it is now the two have come together. And so what we can say is we know that the mass fraction of the A in this final mixture is the amount of A, which is 8 kilograms, divided by 8 plus 4. And so that, oops, that should be an 8. That it, 8. 8 plus 4, so it's 8 over 12, or 2/3. And so the mass fraction of oxygen in the final mixture is 8/12, or 0.666. We also know that the mass that occupies this particular state is 8 plus 4, or 12. We'll just go ahead and put that in as 12. We also know that that mixture fills the entire volume. And so the entire volume is volume 1 plus volume 2. So now that we have the 12 kilograms occupying this volume, it then calculated the specific volume for this mixture of the two gases. And so since this is one independent property, all we really need is a second independent property for this particular case. And what's going to happen in this particular problem then is the energy, the specific stored energy is going to be constant. And so when we first start, we have oxygen with a certain stored energy. We have nitrogen with a certain stored energy. And then the final mixture has that same amount of total stored energy. None of that energy leaves because in this particular case, the mixing was done as a insulated rigid tank. So no work, no boundary work, as well as no heat transfer. So that gets put in through the process panel. And so the process panel allows for state 1 to be the before state, state 2 to be the before state. These two combine together. We remove the partition, or we open the valve, and we end up with state 3. And as we do that, we know that there's no heat transfer, so the Q is equal to 0. And we also know that there's no boundary work that's occurring. And so we see that all gets calculated. And as I said, it's this term right here, which is the conservation of energy, that you have the stored energy times the mass of A, the stored energy times the mass of B, all added together being equal to the stored energy of the final mixture times the mass of the final mixture. No heat transfer and no work. And so that is our conservation of energy. So if we do a supercalculate, we then can go back to our state panel, and our state panel then will be able to solve for the temperature through that energy equation. Knowing the temperature and the volume, then it can, for this mixture, it then can calculate the final pressure. And so we see the final pressure is, since it started out at the oxygen at 100 and the nitrogen at 180, because there was a little bit more oxygen than there was nitrogen, we see the final pressure is weighted toward the 100. So the answer to this particular question is that the temperature, The final mixture temperature was 30.01 Celsius, and the final pressure was 118.2. And that